So I will start, go ahead. Terry already introduced me, so I won't lose any more time. You have here, follow me on Twitter, either on my personal account or for Labs, for updates on this kind of topics if you're interested. Let's go to it. What is the plan for today? I really want to give you a gentle introduction to modern tools and concepts and practices of binary deobfuscation. So the format will be doing a very brief lecture with just explaining roughly the things I will be dealing with on the following live coding session, where I will be going from some dump unobfuscated code. We will be seeing how to apply mixed Boolean-Arithmetic transformations to get into an obfuscated version, and then using some tools and techniques from SMT analysis to reason about the semantics of such code, symbolic execution to retrieve the formulas for obfuscated code from an assembly version, and also program synthesis, so we can actually learn the semantics, the behavior of some obfuscated code, regardless of its syntax behavior. We'll take a look at all of these topics. The main goal here is for you to understand, as I said, all the basic codes, the concepts and approaches, and mostly so you can demystify some of the magic that is around such tools, such techniques, such approaches. I will be really doing a lot of manual stuff, but it might get pretty tedious if you think about doing that iteratively. You would, of course, automate many of the stuff I will be showing you, but my idea is not that I'm going to show you some tools and how to use them and, okay, let's believe them and let's think that it's magic. I want you to understand what we are doing and the ideas behind the obfuscation and the deobfuscation approaches we will be seeing today. So first of all, a couple of words about mixed Boolean-Arithmetic, which is my favorite thing within the research field. But I will be super brief and schematic to the point. Essentially, a mixed Boolean-Arithmetic expression is an algebraic expression, if you want, which is composed of both integer arithmetic operators like the addition, subtraction, multiplication, so on, and also bitwise operators or Boolean operators, logic operators, however you want to tell them, ands or XORs, nots. Here you have a pretty simple mixed Boolean-Arithmetic expression. The idea why we are interested in them is that we can leverage such expressions to obfuscate the data flow of code by applying either rewrite rules or also function identities that complicate, that obfuscate the expression that we want to obfuscate, to conceal, but we will preserve its semantic behavior. So the behavior of the expression itself, the code itself, will be exactly the same. Okay, so the idea behind obfuscation with MBA expressions is that the combination of the operators from those different fields, from the fields of Boolean operators and arithmetic operators, they don't really interact well together from a standpoint of dealing with them as a general theory or applying rules for distributivity, factorization. So this fact that of them not interacting really well motivates the underlying obfuscation capabilities of such expressions. And what we want to do is, okay, we have an MBA expression, we want a simple expression, and we are interested in generating an equivalent expression, a semantical equivalent expression, E2 we set here, which is, of course, syntactically more complex in the formal writing in the number of terms, but that preserves the semantic behavior, that does exactly the same, in other words. The most basic idea for such obfuscation, and the one that we'll be exploring today, is MBA rewriting, which is essentially we will rewrite some operator, some expression with another expression, which is more complicated. Here you have a super basic rewrite rule, where we will rewrite the sum operator, the addition, with that other expression involving XOR, multiplication, and also AND operators. Okay, let's now talk super briefly about SMT analysis and SMTs. Just before going to that, again, this is a super brief lecture, so you know just a little bit about the concepts, but in the live coding session, I will be going again over this and re-explaining everything that might be not super clear here, so you will see in real life. So with SMT analysis, in a nutshell, an SMT solver is a kind of special black box which does this thing actually does some magic, but the idea is we have a tool, the SMT solver, which find satisfying solutions to a set of constraints. Okay, so the basic outcomes that such SMT solver has are either SAT, which is okay, I give you a set of constraints, some set of variables, and some set of numeric values, some set of relations between them. And the outcome of such constraints might be, okay, this is SAT, which means there exists a concrete assignment that satisfies the constraints. It can also be unsat, where no solution is possible for the given set of constraints, but it can also have an unknown state, which is usually what happens when, this is the way of representing when we are out of resources. Usually we end with a timeout. So when we have a SAT outcome, actually we have a concrete assignment. It's not only that we know that those constraints are possible to be satisfied at the same time, but we get a concrete assignment for the set of constraints that satisfies the set of constraints, which is known as a model. You will see now in the live coding that we will be working a little bit with the Z3 SMT solver using its Python API, which is pretty easy to use and understand. Here you have a super basic example of usage of an SMT solver, so you can understand when I'm talking about constraints, what kind of things we are doing. So, for example, here we define X to be a bit vector, 64-bit size. We define the solver, and we add 3 different constraints, which are the constraints, the conditions of the different conditional expressions within the code. When we check for the satisfiability of those constraints, then if those constraints are satisfiable, we would get a model which is a concrete assignment for those set of constraints. Okay, we'll take a look at using Z3 later in live coding for some semantic equivalence mostly. What are the uses, the program analysis uses for SMT solvers? So as I've been saying, we can solve different set of constraints. We can also do model counting, which is okay, how many concrete assignments are that satisfy a given set of constraints. We can check for the semantic equivalence between 2 different expressions. We can also produce inputs that satisfy some set of constraints. So we are interested, for example, in crafting an input that satisfies a given path in the function that this input is received, and so on. Now let's talk a little bit about symbolic execution, just very brief notions. The basic idea is that symbolic execution is just really a computer algebra system which targets programming languages or assembly languages or even intermediate languages or representations. The idea is when we say, okay, what is this computer algebra system? We are transforming the control flow and the data flow of the program, of sections of the code, into symbolic expressions. Okay, then what can we do with such expressions that have been derived from the code? We can, for example, extract the path constraints that encode the branching condition of a basic block with respect to the variables involved in such basic block. So we have in code, in assembly code, for example, conditional jump. We could encode which are the constraints that are responsible for this branch to be taken or not in one direction or in the other direction. We can also, more from a data flow standpoint, extract the formula for a value of a variable. And here you can think of a variable in assembly as a register or a memory position. So with symbolic execution, we are able to extract the formula for the value of this variable at some point in the program with respect to the inputs defined at the starting point of the analysis. You can think, for example, extracting the, what is pretty common we'll be doing is, okay, we are defining, we are interested in the value of the RIX register on x64, Intel x64, which calls the return value. So we're interested in determining what is the symbolic, the expression that gives us the value of the return register of a function with respect to the input variables, with respect to the input registers, for example, the arguments received for that function. We'll take a look at that as well. The idea here is like, it's pretty natural to plug an SMT solver within a context of a symbolic execution. For example, in the first case that we talked before on encoding constraints for paths, for a given condition on a path branching, the idea here is, okay, we extract these constraints, this formula, these symbolic expressions for these constraints with the symbolic execution engine, and then we fed an SMT solver with them to prove, for example, the satisfiability of such a set of constraints, a set of branching conditions. This is pretty useful, for example, on Deobfuscation, when we want to detect opaque predicates, which are essentially branching conditions which are known to be either true or either false always at all cases, so they are put in there only to mess with the code, to obfuscated code. So we can extract the conditions for that path, that branching in the path, and we, with the help of an SMT solver, detect, okay, this condition, this set of constraints cannot be satisfied and never. So we know that the path corresponding to the set of constraints will never be taken, so we can essentially get rid of that. In the context of data flow, which we'll take a look today, we plug the symbolic execution engine to extract the formula for the return value of a function, for example, as I was mentioning, and then we can plug this, we can feed the SMT solver with this formula for a different number of reasons. So we can craft a valid input that gives us the desired output. So we can, for example, simplify the expression that receives the output variable. So we can maybe verify some property of the return value. Okay. What are the limitations of symbolic execution approaches? Mainly the fact that an attacker can increase arbitrarily the syntactic or the algebraic complexity of the obfuscated code. One of the ways is through MBA transformations, but also if it includes a lot of branching condition, it can easily lead to path explosion, the problem of path explosion, pretty common in symbolic execution. Also, there are ways to get around it, but that's not a topic for today, but we could talk in our time about them. And the point with an attacker being able to arbitrarily increase the syntactic complexity, this algebraic complexity, especially in the context of data flow obfuscation, is that, and when we plug such expressions into an SMT solver, into an SMT analysis approach, then this approach won't scale really well because we are increasing the amount of information, the complexity of the expressions that the SMT solver has to deal with, which is not something really manageable at an arbitrary scale. So now let's talk just a little bit about program synthesis, which derives naturally from what we were talking. The idea is that, okay, we want to reason about the semantics of the code instead of the syntax. So we don't care about the syntactic representation of some code, presumably obfuscated. We want to reason from it only from a semantic point of view. Okay, so the idea with program synthesis is that that process of somehow automatically constructing programs that satisfy a given specification, okay? And when we are referring to specification, it's like, okay, we need to tell the computer what it needs to do, and the implementation details will be carried out by the synthesizer. How can we tell a computer what to do? There are several ways. For example, with some form of formal specification, some logic, as you have here, first order logic, where we say, okay, for all x in 64-bit value, then we want to synthesize a program p of x, which does the addition of x plus 7. we could also give as a specification a set of input-output pairs that describe the program behavior. In this case, as you can see, we have a set of input-output pairs, 0, 7, -4, 4, 3, which describe the program behavior. Okay, so in this case, the input-output pairs are related by the fact that the output is always the input plus 7. Another way will be having a reference implementation, which we call an oracle, which we will be using to generate those input-output pairs. And even if this might seem a little bit strange, because yeah, if you have a reference implementation, why you want to synthesize that? This is especially what we are interested in doing when dealing with code obfuscation, because we have a reference implementation, the obfuscated code, from which we can generate input and output pairs of data, so we can extract its behavior and then use those input and output pairs to generate a simpler version that encodes the semantics of the behavior of such obfuscated code. So as I was saying, we want to learn the semantics of some obfuscated code, some obfuscated expression. We can have such obfuscated code with its syntax, its complexity arbitrarily increased, as we were saying, with, for example, MBA transformation, to the point where an SMT solver is really not enough to adequately simplify such obfuscated code or even attempt to verify any properties of this code. Okay. So the synthesis approach is our problem for code deobfuscation, for expression simplification, if you want to think in the expression realm. It leads not quite naturally to fashion a kind of flavor in program synthesis, which is called the oracle-guided program synthesis, which will use the obfuscated code, as I was saying, as an input-output oracle. So essentially, super roughly, we'll generate a set of input-output pairs from the obfuscated code, and then we can trying to build the best candidate program that matches the input-output behavior. Okay, there are several approaches on how to build such candidate programs. There are some stochastic programs, some enumerative programs, some ways of making an SMT solver produce candidate programs as well. Okay, so there are like many ways of dealing with generating such candidate programs and determining which is the one that makes the best input-output behavior match. The method we will be using is probably the one that works best now. Super recent research which uses some offline truth tables for an enumerative based generation of the candidates and the synthesis process. Some of the limitations of these approaches on program synthesis, especially in Oracle-based program synthesis, is first of all trying to synthesize code expressions which are inherently complex from a semantic point of view, not only from a syntactic point of view, but from a semantic, from the behavior itself. Think, for example, in any strong cryptography primitive, anything that has a great deal of confusion and diffusion encoded, it's very difficult that we can encode its semantic from an input-output description into anything reasonable. And of course, it also puts the challenge of how can we generate candidate programs for semantically complex programs themselves. Okay, so another point, another limitation might be non-determinism. Of course, we are producing input-output pairs to determine the behavior of our obfuscated code, and the code we are trying to synthesize to learn their semantics non-deterministic, which means that for the same input, the output is not determined, it's not guaranteed to be always the same. Then there is really no point in trying this approach. Then there is something which are called point functions, which are a particular set of functions which return the same input for all the set of, which return the same output for all the set of inputs, except for maybe a single distinct input or a couple of distinct inputs. So those are also quite hard to synthesize from a program synthesis point of view, because the input-output sampling would be quite not really optimal. It would probably end up being just some constant function, always retrieving the same output, because we might not reach the distinguished finite set of inputs that produce distinct outputs. Okay, so this was a super brief lecture. Don't worry if there is something that you didn't get 100%. I just want to introduce you the concepts, the terminology I will be using for this live coding session. I will be going with you and explaining everything that I'm doing, and you will be looking at it as I am doing. So, okay, first of all, let's create. Yeah, I was already creating it here. Okay, let's create a new file. It's called scramble1.c. Yeah, we can remove this one. Let's just include some headers for types that we will be using. Now, we will be doing super basic function, and we'll be then obfuscating it, retrieving its expressions through symbolic execution, and retrieving its semantics as well. So it will be, we'll start from very simple, from a very simple point, but I really want you to understand what we are doing all the time, so you can extrapolate and really get the important information that we are, of the things we are doing here. Yeah. Let me just move this away a little bit. So we have a function, we will call it scramble, which it just takes a couple of 64-bit unsigned integers, returns also an unsigned 64-bit unsigned integer, and for example, we'll say, I want you to return this function. Okay. This is a function which will simply take the couple of inputs and return the addition of the result of ORing the two variables and then XORing the two variables. Then just adds up those results and returns that. And just for the sake of completeness, so we can run this. We'll just print the result for an example. Yeah, I think it was that way to print unsigned integers. I don't know. Okay. If we need the terminal, we'll get that. Okay, cool. So it is the first function. Let's just okay, where is the terminal here? And we'll probably move it back. Let's just compile it with no optimization. I'm just removing the optimization so you can better map the C code with the assembly that we will be looking at for no other reason, honestly. Run it. Yeah, okay, so it would just returns the result of this computation. Okay, now let's obfuscate this expression. Let's use some MBA rewrite rules to obfuscate this expression. Let's jump into Jupyter. I have prepared here some rules. Okay, this is the original expression we had, and I will be using these rewrite rules, okay? This will be the rewrite rules that we will be using. And you might be wondering, okay, but where those come from? This is, we have methods, I would say we have methods to generate those. They are quite easy to use, not trivial to explain at all. We would need like 2 hours entirely to explain methodology to generate such. But honestly, you have listings of these rewrite rules if you want to use them without worrying about that. I can share with you resources afterwards where you can find different sets of rewrite rules and also references where you can find a methodology to generate them on your own. Right now, I will be just using those ones I got. So we won't lose like an hour trying to explain how to generate them from scratch. Okay, so what we'll be doing first of all is using an SMT solver, using Z3 to actually prove that these rewrite rules are valid, which means that the simplified version is semantically equivalent to the obfuscated, the complicated version. Okay, so we will just import everything from Z3, which is the SMT solver. Then we will define X and Y to be bit vectors with those labels on 64 bits in this case. And then, okay, let's prove for the OR. We have a nice macro on the Z3 library, Python library, which allows us to just prove. And call proof with this expression, this other expression, and we will do the same for the rest. This will be the XOR. This will be the addition. Okay, we run this, and yeah, we got the 3 of those approved, which means that the SMT solver Z3 has been able to check, to verify the semantic equivalence between all these 3 pairs of expressions, from the simplified ones to the more complex one. Okay, now let's generate, prepare a way of getting the original expression and applying these rewrite rules iteratively. Maybe we'll do a couple of 3 iterations to see how far we can go. It grows really, really fast, the obfuscated expression, you will see. So let's just call or this is this one. I'll be using just strings. In this case, I'm interested in replacing the variable names. You will see why in a second. It's just from a practical standpoint, it's easier to not mess up when replacing in the expression that is being obfuscated, not have both the expression we want to obfuscate and the rewrite rules using the same names for the variables, because otherwise they mix together in the process and it can be quite a mess. But essentially what we are doing here is just expressing the rewrite rules and using L and R, because you can think of this as the X variable to be the left variable, to be the variable at the left, and the Y variable to be the right variable at the right. And this will make a lot of sense. In a second, we'll be using some abstract syntax tree representation of such expressions to actually deal with the obfuscation process. Let me just put the rest of them. We'll do exactly the same replacement. Let's just print them. Okay. Right. Yeah, so this is exactly the same rewrite rules. I'm just replacing X for capital L and Y for capital R. You will see in a second why this makes sense in the context of representing these expressions as abstract syntax trees, as syntax trees for the meaning of the expressions. You might be thinking, for example, hey, why can't just we use something like dirty replace or even regex replacing to make the rewrite rules? And you could do that. You can actually do that. The problem is that this does not scale if you wanna apply these rewrite rules not only to single variables but to expressions themselves. And what I mean by that is that if you, instead of wanting to obfuscate X plus Y, you want to obfuscate whatever that goes here, another expression plus another expression, you could substitute the whole expression every time in here, okay? And the whole expression at the right every time in here. And this is something that we can easily manage, representing the expression as an abstract syntax tree, which is quite painful, and I would say not something you really want to do with dirty just regex replacing or Python replacing or anything like that. That's why we really want to bring the power of an abstract syntax tree. And this is a consideration, an entirely practical consideration for you. From a theoretical point of view, you don't, I mean, it's not interesting if you are replacing with regex replacing or with abstract syntax representation. But from a practical standpoint, using an abstract syntax tree, as we'll be doing in a second, allows us to make the rewrite rules not only apply to single variables, but to sub-expressions themselves. We'll see that in a second. Okay, so as I was talking about the abstract syntax tree, we'll be just importing required packages. This is the abstract syntax tree and the unparser, which comes apart from the actual module. We're going to define the the original expression if you want. We had it here, right? Yeah, I think I had it here. Yeah, just copy paste. Okay. And then we are going to parse this string into an expression. We're going to simplify it with eval mode, which is a fancy way of saying, please parse that as if I was evaluating the expression itself. And then we can print the actual AST representation of the parsed expressions. You will see what it looks like. For example, for indentation. Yeah. So now this expression is represented as an expression whose body is a binary operation, which is an operation with two operands, the left operand and the right operand. This is motivating the naming here. So the expression is actually a tree with the root node is a binary operation. The root node has a left node and a right node. The left node is another binary operation, which is actually operation of kind or bit or, which is a bitwise or. On the left, it has the X, the ID X. On the right, it has the ID Y. The operation itself for the root node is an addition, which is, you can see here. And in the right of the binary operation, the global binary operation, the addition, you have another binary operation, which is the bitwise XOR. So you can see here. And again, the left part of the bitwise XOR is the IDX, which is the variable, which is the expression itself at the left, and at the right, we have the Y, okay? Why we are expressing it this way? Because if instead, as I was saying, if instead of having here X and Y, you would have another more complicated expression. Here we could reason about it in the sense of a tree, in the sense of, okay, let's not only apply the rewrite rules to the single variables, but also to expressions themselves that can expand in a way bigger form. So what we want to do right now is essentially construct a way of parsing this, getting these expressions from leaves to root. I'm interested first in obfuscating, in applying the rewrite rules to the leaves. The leaves will be the XOR and the OR, that is those operators, the leaves understanding the expression as a tree. So at the node of the root node of the expression is the addition. This addition has two childs. One of the child is an OR node, which has a couple childs, which are the X and the Y. The expression it is ORing together. The other child has an XOR expression, and this XOR expression has another two childs, which are leaves as well, which are X and Y again. So I'm interested in obfuscating from the bottom up. So first we will obfuscate XOR Y and X XOR Y, which are at the bottom of the tree. You think of that as a tree. And once we have obfuscated that, the result of those obfuscation will itself be represented as the left and the right parts of another binary operation of the addition operation, which will obfuscate afterwards. In this manner, getting all the power from the abstract syntax representation in order to obfuscate not only for single variables but for sub-expressions themselves. So let's build I don't know how to call it, bottom-up BFS traversal of the tree. I would just call it that way. We'll receive a node. Let's just define a queue of the nodes to process. Append the first one. And we will need a list which will hold the binary operations, that those operations that we will be obfuscating. In this case, there are only 3 operations which we are treating with rewrite rules. How do we need to store them someplace? So while we have some nodes to process, we'll define the current node to be popping the queue of nodes. Yeah, from the start, it will be better. Then we will have to check if this node, again, the nodes we are dealing are of this kind, are binary operation nodes from the IAST representation. So we want to check if they have the left attribute and also the right attribute. Okay, and this will fill with, yeah, if they have left attribute, we will just append it to the nodes to process. Here the same. And finally, if the current node is a binary operation, is instance, yeah. Yeah, actually, this is not node, this is the current node that we are, yeah, the current node we are dealing. If this is an instance, the current node that we are traversing on the AST representation is a binary operation, then we will just save it in our list. Typo. Yeah, I tried this yesterday. I think everything should be exactly that way. So again, let me recap a little bit. This bottom-up BFS will receive a root node, will be essentially this node, the binary operation, the addition. We'll traverse it in a way that every time we are branching left and right, we are checking that those nodes exist, and then if those nodes are instances of another binary operation, for example, at the left here we will have another binary operation which is bitwise OR, and on the right we'll have another binary operation which is a bitwise XOR, then we'll just append it to our list of binary operations we are saving to obfuscate later. Now let's define our actual functions to rewrite with the MBA. Rewrite rules. So we'll take a root node. Okay, so this will take a root node. The first thing we will do is get the binary operations that we will be applying rewrite rules to. So this will receive the root of our expression, which is the operation at the top of the abstract syntax tree representing our expression. And where we have those will probably now let's define a new. Okay, we get the current one, so we'll be popping, which means that we will be getting from the bottommost, from the ones below. In this case, the first ones that we'll be getting would be the XOR and also the OR, the bitwise OR. And we will create a new node. In this case, we'll put it to node at the beginning. Now we will obtain the left part of this of the current node, which is the left branch of the current node, by unparsing. This is just the string. The AST unparse will just retrieve the string representation if you want. Same for the right. And if I remember correctly, it is included a new line, so I'm just removing that. Now, again, similar as before, if the current operation is an instance of the bit OR, which is one of the operations that we're considering, then we will treat it. The same goes for the XOR, and the same goes for the addition. So we will treat these ones. So here we'll create a new expression. We'll take a moment to see how can we create that. But essentially what we'll be doing is, okay, if the current node in the abstract syntax tree representation of the expression is an operation of kind bitwise OR or bitwise XOR or addition, then we will build a new one that will replace the current one. Okay, so if we generated a new one, then we'll just replace the operation left branch and the new and the right branch. Now, how can we replace that? So essentially, we will encode here the abstract syntax tree representation of the result of applying the rewrite rule to the left and right parts of the actual operation, the current operation we are dealing with. Okay, so this is why we are, again, I want to emphasize we're using syntax tree representation instead of silly string replacement, because we will be able to replace not only at the level of single variables, but on the level of sub-expressions that are added together or get XORed together, okay? So in this case, we will need to construct expressions, we will need to parse, and what is the string that we want to parse? Here, we will actually get those rewrite rules that we got before in string representation, and we will replace in them this left and right, this X and Y, left and right containers, placeholders with the left and right representations of the expressions of the current binary operation we are dealing with. For example, for the OR, and this will be replacing the so this will essentially replace the L character, the L placeholder, with the actual expression that has been retrieved from the left part of the operation in this case, and the same we'll do with the right. This should be in mode eval as well. And get the body. Yeah. So we're going to do pretty much the same. I'm just going over it another time just before continuing. Okay. So what are we doing here? Essentially, we are retrieving the binary operations of the expression we are interested in obfuscating, in transforming. So, and then we'll be processing these binary operations from the bottom map, so from the leaves of the true representation to the node of the true representation. We'll be getting one at a time. And for each binary operation, we'll get its left part of the expression of the binary operation. So if it's an addition, the left part of the addition and the right part of the addition, the same for the other kind of operators. So the left and the right. And then for the kinds of binary operations that we are dealing right now, which are only the bitwise OR, the bitwise XOR, and the addition, we will construct a new node, a brand new node in the AST representation, which will be the result of replacing or applying the rewrite rule. This is essentially applying the rewrite rules that we have defined to the left part of the operation and to the right part of the operation. All the other things are essentially syntax sugar for the AST model to work fine. Okay, so don't really worry about that. You really have to understand that we are getting a binary operation which we want to obfuscate. This binary operation, for example, if it's a bitwise OR, we will get the left part of the current binary operation of the OR and the right part of the OR, and we will substitute. We'll apply the rewrite rule, substituting the left part and the right part into the obfuscated, the rewrited expression, the more complex expression. Okay. Actually, let me. We're gonna execute that right now, but let me print at each step what is happening, so you will visualize really nicely. Expression. Yeah. If I didn't make any typo, then we should be able to call that. Okay, so we have the expression defining here. We have printed it in the AST representation, which is root, which is a binary operation, which branches left and right. The left is another binary operation, a bitwise XOR. The right is another binary operation, the left bitwise OR and the right bitwise XOR. So when we apply that, we'll have to rewrite MBA to the expression. Yeah, I think it was that way. Yeah, exactly. The body of the expression will essentially get the root node. And it will print that. Yeah. See here what happened, okay? So it first applied the rewrite rule for the XOR. Okay, so let's just make it more explicit. I really want you to follow what's happening here, so I don't mind putting dump print statements here and there. Yeah, let's probably run from here. So the expression starts from the beginning. Okay, the XOR rewrite, check that this remains exactly the same. This part, the OR part, remains exactly the same. And we are applying it, we are applying the rewrite rule to the XOR part, okay? So this is the result of applying exactly this rewrite rule, okay? So we are essentially replacing the XOR part with a rewrite rule. Now, what happens again, let's go to the OR bitwise. Now, okay, we now have that. This is the result of the rewrite rule on the XOR. Now we'll apply the OR rewrite, and we'll generate essentially this another expression, which if you see the rewrite rule is essentially what's happening here. Yeah. So this is rewriting the OR with this another expression. But then what it's pretty interesting, and the whole reason I've been doing all these maybe a little bit tedious AST manipulations, is that now we can apply the addition rewrite rule to the different parts, of the addition, not only to the variables themselves. So what's happening here in the addition is that it is considering this to be the left part of the addition, which is here, and this to be the right part of the addition. And the rewrite rule is being applied as if this was our original X, if you want, and all of that was our original Y, if you want. So that's why this rewrite rule, this add rewrite rule, increases so much the obfuscated resulting expression. That's because we are applying the rewrite rule to whole sub-expressions. Okay, so this is really the point of we want to manipulate that not in a dump regex replacing manner, which can be done and it's pretty quick and it can work. But if we want to be able to apply those rewrite rules to whole sub-expressions, considering the rewrite rule not only applied to a single variable, but set of sub-expressions, then we need some kind of abstract syntax tree manipulation, which is what we've done here. And you can observe the result of doing that here. Okay. Now, you may be thinking, yeah, are you sure that this is equivalent to the original expression? So let's just check it again with SMT. Again, it is probably defined again from before, but just define again just in case. So the simple expression in Z3, it was, this is our simple expression, our original expression, if you want. How do you want to call it? I don't know. Obfuscated. So, this whole expression. Okay. Yeah, this continues to the right. And now let's ask Z3 to prove that the first expression is actually semantically equivalent to the second expression. It might take a little bit, not that much. It shouldn't be that hard. Yeah, that's it. It's proved. So now you have guaranteed, of course it worked because the rewrite rules are valid. You didn't really need to check that, but so you can take a look at how can we use those tools, how can we manipulate SMT solvers to prove things for us. Now you can be, you can guarantee that the original expression that we wanted to obfuscate and this quite more complex expressions that we have generating by applying just 3 different rewrite rules, but as we have been able to apply, in this case, the addition, not to single variables, but to sub-expressions themselves, this grows really fast, okay? So let's just now create, well, let's make a couple more iterations in here. Yeah, I'm just probably gonna comment this here for all these steps, otherwise the output can be pretty massive. Yeah, so we're gonna rewrite again. Oh, sorry. Yeah, let me execute from here so the expression, the original expression gets defined correctly. Yeah, here I will print and this can probably go away as well. Okay. I'm just gonna comment this in case we need to run this again, so we have not to wait another 10-15 seconds for it to be proved. Yeah, right. So let's, okay, now apply another rewrite rule and print the resulting expression. Okay, this grow quite a little bit, right? At this time, I won't be doing this check. I'm pretty sure it should be able to prove that semantic equivalence, but you might need like 5-10 minutes easily to leave the SMT solver to prove that. So I really want you to show the way that I'm showing you this semantic equivalence, that you see that the SMT struggles as we increase syntactically the complexity of the expression, but semantically it's exactly the same, okay? So I won't be checking again, because again, we should need to wait 5-10 minutes, but you could try to do so, and after 5-10 minutes, it would also be proved. Now let's make maybe just another iteration. And this will grow pretty big. Yeah. Okay, this is insane right now. We won't go more than here. This is actually an insane function. And you might try to plug an SMT solver to prove the semantic equivalence for that, but I can guarantee that this like will never finish, not in a reasonable time. So here, what we have been doing is, okay, just using 3 super simple rewrite rules, MBA rewrite rules, we have been able to transform our original quite simple expression, the one that we have here, into this more complex expression. This even more complex expression, this is actually like, you don't really understand what the hell is going on in here. And this monster, like, of course, you don't have any idea what's happening here. And this has only been done with 3 super simple rewrite rules and just performing 3 iterations of this process, because as we are able to apply these rewrite rules to the sub-expressions, this grows extremely fast. This grows exponentially. If we would make like just another iteration, which I won't do that, but it will, I don't know, but it will be pretty massive. It might actually crash the screen. Okay, so we have been like taking a look now at MBA transformations and plugging SMT solvers to try this thing. But okay, but what about the code? What about the actual code, right? So let's generate 3 C files more with. We'll plug these expressions. We'll literally plug these expressions in them. So let's just copy, scramble. 3 copies. Yeah, another copy. Okay, this will be scramble 2, scramble 3, and scramble 4. Okay, so this the first one, scramble 1, is the expression we have seen. Scramble 2, we will place this one. Okay, scramble 3, it will be this, another one. Yeah, here you see, well, quite some big. I have like the font pretty massive, so everyone can take a look at that. So that's why maybe it's not fitting everything in the screen, but you get the idea of this is actually a quite massive function, and even more the number 4 that we are actually trying, and we'll try the one. It should work pretty finely. Apart from the editor taking up all the screen, it should work with no problem again. yeah, so this makes no sense. Just take at the summary here in the right of the VS Code screen. So this is the whole function we are actually using. As I said, I'm just gonna compile them, all of them. So one thing that you can check, even if we are not proving semantic equivalence for the bigger ones, because the SMT simply couldn't handle that, is that, well, the results seems to be, yeah, they seem to be like the same. And we are, of course, only checking what input, but anyway, it seems to work pretty reasonable. And we can actually take a look at the assembly representation. So you can see that it's not only that in the C code, this gets more complicated, but this is also translated in real life when you find some obfuscated assembly code. Let's take a look in assembly. This here, I think. Yeah. I will just take a look in R2. To print the disassembly of the function scramble. So this the disassembly of the first one, the non-obfuscated one. You can essentially reconstruct the expression just at plain sight. It's loading the first two, the parameter from RDI and RSI registers into those memory location. Then it's just ORing one with the other. So it loads the first one into RAX, and then it ORs that with the second one. Then again, makes the XOR with the two parameters again. And finally, the result of the OR operation and the XOR operation adds them together and simply returns. So this is pretty simple, and we can actually take a look in the decompiler if you want. It will basically give us this very same, it will essentially give us the very same expression we have. Okay. Yeah, it's hang. Oh, here it is. Okay. So yeah, well, essentially XORing in addition to the OR operation. Okay. We can, of course, take a look to the second one. We're going to do exactly the same. You see here, the second one, the assembly code is not that trivial at all. So this is not, we can't really see what's happening here to the return value with respect to the input values. Okay, I don't expect you to read right now the assembly with me. I'm just scrolling a little bit up and down so you can make yourself an idea about the dimensions of the obfuscated assembly code. This is just for the second one. And again, I think we could try to decompile it as well. It'll take a few seconds, but it should give us a pretty nice representation of it. But again, in an obfuscated manner that we can really grasp the behavior of the code. So this is the obfuscated representation, the decompiled representation of this obfuscated code. We can do the same for the third, which I'm just gonna skip for the sake of brevity. Just take a look at the fourth, which is the biggest one. And here, yeah, when I tell it to print me the disassembly of this function, it warns me, you really wanna print 1,805 lines, which is the number of instructions of this disassembly. So you can see this is massive. Just take a look at the scroll bar. You can see this is massive. I don't expect anyone trying to understand anything from here or reading. I'm just scrolling up again and again and again and again and again. So this makes no sense. I mean, if you find that, you have no idea what the hell is going on. You really don't have any idea what this function might be doing just from reading assembly. Okay, so here we are. A massive function in assembly. I think it should be able, the decompiler, to retrieve it in a nicer form if you want, but again, it should be pretty massive as well. Usually the decompilers apply some optimizations on their own, which reduce a little bit, which might reduce a little bit. But anyway, it will be pretty massive. Yeah. Well, you can see this expression makes no sense at all. So, okay, it's shorter than the assembly, okay, but again, you have no idea what's going on here. So you don't understand anything of what's going on here. This is the obfuscated, decompiled version of this obfuscated expression, okay? But what I really want you to understand is that those obfuscated parts, those obfuscated expressions are built from a simplified one, and they preserve the semantic behavior. All these monster expressions, especially this last one, they behave exactly the same. They are the same expression from a semantic point of view. It's only that it's syntactic complexity. It's complexity from the point of view of the human who is analyzing it, and also the tools that we use to reverse engineer. It makes no sense for us. So we cannot grasp the knowledge, the behavior of such functions, of such expressions, okay? Now let's get back to here. Okay, now we are probably gonna do some symbolic execution to retrieve these expressions from the assembly in a symbolic execution manner. I'm just gonna place here a kind of separator. So the first thing we'll need is a way of extracting the formula, the symbolic expression for the output variable, for the return variable of these assembly functions. In this case, we only have, these functions are quite simple in the sense that even if they are massively obfuscated, just a single basic block, there's no constraint on that other than for like pedagogic reasons, to limit the scope of what we are dealing in this session, but this will make our life a little bit easier. So I'm gonna use miasm, which is a symbolic execution framework, to do this, to extract this formula for the return register after symbolically execution this function, this single basic block in this case. So I'm gonna import everything. Analysis, binary, the container, analysis, machine. Yeah, I have the cheat sheet in the left monitor right now for this code, but you will have it again. Yeah. I will walk you through the code that we are using, so it's pretty self-descriptive. Now I'm just importing a couple of stuff needed. Yeah, here we will just be importing things that we need. We need the binary analysis module from miasm. We need the container for a binary. We need also the machine abstraction for the architecture. We need the location DB. Which is the way of dealing with the positions and so on, memory. And then, of course, we need the symbolic execution engine actually for the intermediate representation in which miasm represents the expressions that it's lifting from assembly to its own language. Again, I'm not expecting you to understand 100% what is doing miasm here. I just want you to understand the idea of symbolic execution in which we can get from a language, in this case assembly language, in particular 64-bit Intel syntax, Intel architecture. We can lift that, we can translate that into in this case an intermediate language, which is then particularly from miasm. This is a miasm intermediate representation. Reason about it in this intermediate representation, which is essentially a way of expressing the actual value of the return register we were interested with respect to its inputs. Okay, so let's define a function which will be get RAX expression which will receive a file path and then a start address. And as you can guess, we will have to pass here the file path for the executable that we want to deal and the address for the function that we want to deal. We want a symbolic execution. In this case, the address of the function, which is the same address of the basic block for the scramble function in any of the files we have been taking a look. So we need the symbol table for the symbolic execution engine. This is the symbol table. Just a couple of comments here and there. Then we need to create the machine abstraction. Sorry, we need first the container, of course. For the binary, we need to load the binary. We'll just open the binary, the file path of the binary, and read binary mode, and then the actual symbols to the location, to the symbol table, the logtb. Now we can construct the machine as the architecture of the binary that has been loaded in the container. In this case, will be the architecture, 64-bit Intel architecture. Now we need a disassembler engine. Yeah, again, just need the symbol table. We will need the lifter, which is the responsible to get the disassembly into the intermediate representation for miasm to deal with the code that we are essentially treating in this case. Again, don't worry if you are not understanding all the miasm internals. It's not really the point of today's workshop, but I wanted to show you a real tool that we can use for the symbolic execution. There are other tools, some of them very good as well. You have Triton and others that you could also use for the symbolic execution, your symbolic execution needs. In this workshop, I'm really interested that you understand the concept of symbolic execution. You can see it in action. And here I'm just adding syntax sugar and constructing the engine so we can get the code from the assembly and translate it into an expression. Okay. Also, this code I'm putting here. It's based on some examples that are in miasm as well. So you have guided examples as well to do everything you need. And of course, I will be sharing this afterwards, so you can use that as well. Now, okay, we are going to disassembly the basic block, actually the whole function at the start address. So with the disassembler engine that we have initialized, we call the function this block. We're at the start address. We'll take a look in a moment where is the start address of this function. And if I remember correctly, the start address will be exactly the same for the 4 different executables for the same function. Now we'll lift this assembly representation to the intermediate representation. We'll then first initialize the contour flow graph for the representation, for the intermediate representation. And then again, the lifting is essentially translating the assembly into the miasm intermediate representation. There are engines that perform the symbolic execution directly with the assembly representation, but it's pretty common usually that you have a ground truth, a common place, which is an intermediate language and intermediate representation. So you can essentially make your analysis, all your techniques or everything on top of the same intermediate representation. And when you want to support another architecture, then you just need to construct the lifter, the translator from that native architecture to your intermediate representation. And then you have everything else for free because you have implemented the analysis on everything on top of your intermediate representation. That is why it's pretty common to have these intermediate representations in symbolic execution engines particularly. And also in compiling frameworks, you think of LLVM, it happens exactly the same with the LLVM intermediate representation. Okay. So here we are just with the lifter we have initialized, we're adding an assembly block into the intermediate representation control flow graph, which will be the ASM block that we have disassembled at the start address of the file that we have loaded. We'll be loading them yet. I'm gonna probably use some spaces here to be sure. Then finally, we can initialize the symbolic execution engine, taking as parameter the lifter that we have created and populated with the assembly block, and then we will just simply symbolically execute the run block. I will essentially symbolically execute the code that we have in our intermediate representation on the start address of the function that we have created. Essentially, this will perform the actual symbolic execution. Everything here. This was just syntax sugar, I would say. Well, not really sugar, but logistics in order to build all the context for the symbolic execution engine to be able to perform this single line, which is okay. Now let's symbolically execute this block, this basic block at that address. The basic block will be the basic block of the function of the obfuscated code. Okay, and when we have symbolically execute this, what we'll do is simply return the state, return the expression of the register, of the return register. So we'll simply, on the symbolic execution engine, get the register RIX from the architect, the lifter, the architecture that is defined within the lifter. So essentially, yeah, there's a typo here. Return. Essentially, these are the two lines that you are more interested. The symbolic execution of the basic block where the obfuscated code lays, and then we will just return the expression that after symbolically executing this block, after constructing this passing of the expressions of everything with respect to the symbolic value, and we arrive to the expression that determines the value that the return register will have at the end of this basic block, which is the expression that determines the value of the register RIX, which is the value of the return function, the return value of the function, the obfuscated function, the obfuscated expression. Return the expression for okay. I hope I have not made any typo. I will take a look. So now let's define a file path. Scramble one, for example. One, and the address. Let's just take a look. It was the same for all of the files, so it should, yeah, it should be the same. Is there address is 1149? It was right. Now let's get the expression for the RIX register for the scramble one. Let's just call the expression we have defined. We'll pass the file paths parameter as well as the address of the function of the basic block of the obfuscated code. And let's just print that. Brax from scramble one. Print. Let's remove this underscore to match the file name. Just a little bit prettier. Yeah, of course, this will crash because I don't have executed that yet. Okay, we create the function that will get us the expression for the return value, and now we can create that. Okay, what's happening here? Block DB is not defined. Yeah, typo here. Okay, first typo. Okay, here you have it. It's not necessary. So through symbolic execution, we have get the basic block for the function that we are interested. We have symbolically executed it, and we have retrieved the value, the expression that gives us the value of the RIX, the return register, with respect to the input variables. The input variables in this case are RDI and RSI register. So you can see that this is essentially the expression we are dealing. In this case, of course, this is plain because this scrambled one was the original file, not obfuscated at all. Okay. So let's take a look at the same for the rest of the. For the rest of the files, I'm just changing the file names. The address for the functions should be the same. Yeah, here you have the expression represented with the miasm representation here. The not exactly the miasm intermediate representation because it's well, has some particular syntax, but it is the string representation, the printing representation of such expression given from miasm. Okay, so you can see this is the expression for the second the obfuscated expression, the first obfuscated, which is the second file that we generated with this obfuscated part, this obfuscated function. Again, we can take a look at now the third. And I'm saving them, essentially. I'm saving them because I'm probably gonna use them in a moment. Yeah, this should be quite bigger. Okay, here you have it. This is the symbolic expression retrieved from the symbolic execution engine that gives us the value of RAX with respect to the variables RDI and RSI. I know I'm repeating myself all the time with those concepts, but it's just made on purpose, so it really sticks with you. That with symbolic execution here, what we are doing is extracting the formula, extracting the expression that gives us the value of the output variable that we are interested in with respect to the input variables that define it, that play a role in their computation. In this case, the output value is the return value RAX. The input variables are the two input register RDI and RSI. Okay, and let's do exactly the same finally for the fourth one, which will get quite big. But it should work nevertheless. Yeah. So as you can see, it grows pretty fast as well. It comes no surprise. This expression was massive itself. We have seen it represented within the Python string that we generated. We have seen represented the C code. We have seen it represented. We have seen it represented in the assembly language. We have seen it also represented in the decompiled version of the assembly, and now we are seeing it represented after symbolically executing the obfuscated function. So you see that essentially all the time is the same as the sum function, just we are seeing from different point of views, different parts of the whole obfuscation, the whole landscape. I would say we are taking a look at different parts, different steps in the process, and we are seeing how those things are represented at each part, which tools we are using to generate those expressions, read the assembly part, decompile them, and in this section we're actually retrieving the symbolically execution, the formula from symbolically executing this function. Okay. Now, you might be thinking, okay, now what? So the first part, which is, yeah, we are obfuscating, we are checking stuff, but imagine that we don't have access to the source code, of course, which is what usually happens. So when we don't have access to the source code, we start essentially here. We start here in the part of, okay, symbolic execution. So if we retrieve from symbolic execution a function which we're interested in understanding what's going on, and we just retrieve this expression, we could have seen that in the compiler, for example. We retrieve this expression, we say, okay, we understand what's happening, it's pretty clear. If you retrieve this expression, you are not understanding what's happening. So you see quite some things going on involving RDA and RSI, but you're not really sure. If you could spend like a couple days, maybe not that much, depending on how much used to dealing with such expression are you might be able to maybe reasoning about it, reducing at some point, and you could also try to plug an SMT solver, which we'll do in a moment, to attempt to simplify it. But you will see that SMT solvers don't really work fine with MBA transformations. Okay. And of course, for the Scramble 3 and the Scramble 4, you have absolutely no idea and absolutely no way of understanding from the syntactic point of view what's going on here. Okay. So let's plug on the SMT solver again and attempt to simplify those expressions. You would see that it will fail miserably. So we wouldn't really get anything good, I would say. So the first thing that we'll need is translate these expressions obtained through the symbolic execution into expressions in Z3, in the format, I would say, the object of Z3, the SMT solver. For that, we have some really cool utilities from miasm itself, which are the translators. I think it was this one. Translator. Oops. This will just get a miasm expression and translate it into a Z3 expression. So let's say that this was the first one. Okay, this is actually the intermediate representation of miasm. It's just we print it. It prints it in a more pleasing way. Okay, so let's just throw a Z3 the SMT simplification, which does some approaches. It groups terms. It tries to do some known reductions and so on, but you will see that it fails miserably with mixed Boolean-Arithmetic expressions. In this case, it's not obfuscated, but we are going to do that just so you can see how can we use it easily. So first thing we need is to translate this expression into Z3. Okay, let's just call it RAX Scramble 3. And now we are going to simplify. This simplified method is a method that comes when we imported the Z3 at the very beginning, okay? So this does this thing. We will just simply print the output of that. Oops. Okay, in this case, of course, nothing happened because it was already as simple as it could be. We could actually print the original one and the supposedly simplified, so you can take a look. Original RAX. Okay, so here nothing really happened, okay? But let's take a look at second, for example. And here you actually see that it did some stuff. It actually did some stuff. Here, those big numbers are essentially because Z3, when it prints expression, it represents all values as unsigned. So this is really conceptually a quite small negative number, if you want to think it that way, but represent as unsigned, it's that pretty big number. So it did something. So you can tell that here something happened. This is not really exactly the same expression as this one. It's somewhat more simplified. Not a lot, but somewhat more simplified. So this SMT solver did something, okay? But it really made nothing worth for us. It's nothing that we can really use to understand it better right now. It's okay. It transformed it, it grouped the terms. Okay, thanks, but it really didn't played well with it. And if we go to the third and fourth, you will see that the SMT solver fails miserably when trying to simplify, to mix terms, to apply reduction rules to those expressions obtained through MBA transformations. Because as I was saying initially, what motivates the use of mixed Boolean arithmetic transformation for obfuscation is that we don't really know how to deal with them. There's cool research that is being done super recently, and there are some stuff used, and we have academic tools and reasoning that can deal with some stuff like that. But for like SMT solvers right now, they tend to fail miserably when dealing with that. Yeah, okay, so we have here the original one and the simplified, which is, yeah, okay, you grouped some terms, you maybe print it in a maybe slightly better way and putting new lines and so on, so you can read it a little bit better, but not really. I mean, you can't understand anything from here. And of course, if we print for the fourth one, as you might expect, we will end up with a massive expression in Z3 representation, which gives us no information at all. So this was, yeah, the original expression from miasm, which is already massive, and the simplified one, which is, as you can see, just grouping some terms and printing it in some groupings, but you can't really understand anything from here. So the SMT solver, what's happening here is that as we are increasing arbitrarily the syntactic complexity, the algebraic complexity, and when we say arbitrarily, is because, well, essentially we are applying some rewrite rules, and we have stopped at three iterations because we already had some monster expressions, but the degree of this increase of complexity is completely arbitrary. So the attacker or a defender, really depends who's using the obfuscation for what purpose, but can increase this complexity as much as he wants, as much as he or she wants. And the SMTs won't deal really nicely with that. Okay, again, I'm using just Z3, and I'm using just the bare bones simplify function. There are some strategies, there are other SMT solvers, of course, yeah, of course. I'm not just telling that all SMT solvers are all super bad for that, but I would say currently the research on SMTs doesn't really include quite some formal treatment for MBAs in a way that they are useful for practical deobfuscation. And in a way, not because it's not to blame the SMT researchers with those who do an extremely nice job. It's because there is actually not really a lot of research on MBA, reasoning on MBA, abstracting MBA from dealing with them from a theoretical point of view. At the first place, we can actually build tools that in real life can handle them. So that's the main motivation such transformations are used. Okay, great. So we have seen with symbolic execution, we can retrieve the expressions for the value of a return function. We have seen that the SMT solvers don't really help us that much trying to simplify them in general. So we are left with the question, okay, but what if we found some massive function like that, and we really need to understand what's happening? So this is some obfuscated code. we are really interested in happening and understanding what's happening. So we wanted to reason again. Remember that these four obfuscated, the four different versions, the faction, the original, and the three levels of obfuscation, they do exactly the same from a semantic point of view. I mean, when you throw the same input, they will output the same value. All of them. It's just the syntactic representation, the algebraic, the syntactic complexity. It's just increased arbitrarily, but the semantic, the behavior didn't change. I want to reiterate this like another time, and I know I'm repeating with that, but it's crucial. The point that when obfuscating in general, not only with MBA transformation, but in general, we want to preserve the semantic behavior. What we want to do is complicate the life of the reverse engineer and the analyst who is dealing with that, but we want to preserve the behavior of the code that we are obfuscating. And this case is no exception. We are preserving the behavior, the semantics of the code, of the expressions we are obfuscating, but we are representing them in a way, in this case, with data flow obfuscation the way the expressions are represented themselves, so that you don't really have a chance to understand what's happening from a syntactic point of view. So that's why we want to reason from a semantics point of view, which is the whole idea, the whole philosophy, if you want, of program synthesis. When we apply it to program, the obfuscation is like, it comes from the question, okay, but what if we could think and we could reason only about the semantics of the code and don't really care about how it's expressed syntactically. We don't care if it's super simple or a massive monster of expression. Let's just focus on how it is behaving, on the semantics of the code. And maybe we can extract some information from that semantics that allow us to reconstruct simple versions, simple definitions of the expressions of the code that represent this behavior, this semantic behavior, okay? Let's make here a small operator again. So the idea here is we will be using only the semantic information of the code to construct a valid expression, a valid candidate, synthesized candidate program that represents, that encodes the semantics of the code, regardless of its syntactic representation. Okay. For this, we'll be using MSynth, which is a program synthesis tool, which actually implements an algorithm, a program synthesis algorithm for code deobfuscation, which is called QSynth, which comes from a paper from a couple of years ago, which is super cool. And MSynth is one of the public implementations of this algorithm, and I'm using that because it's built on top of Miasm, so it will come pretty natural, and we can reuse actually the things we have used right now. Just a few words about this QSynth algorithm we are using. Is as I said earlier in the lecture, it constructs candidates programs in a way of generating an enumeration, so making an explicit list of possible candidate programs, combining a number of variables with a set of operators, and then checking for each sub-expression of the obfuscated expression, of the complex expression, if they match the input-output behavior to some of the generated expressions that are for 3 variables and 3 operators, up to 3 derivations, for example, so 3 degrees of a combination. Okay, we have we have in the training a model where we actually build such a program synthesizer from scratch, dealing with that, and I can share some knowledge of that with you, and also of course the papers that describe the algorithm and so on, which is pretty interesting. In this case, I just wanted to make sure that you understand that now the tool we are going to be using is going to synthesize, to construct a candidate expression, a candidate code, if you want, with respect to the input-output behavior of the obfuscated code, and not really taking into account, not really caring that much what is the syntactic representation of the code. Okay, so let's just load that. So we'll load the simplifier, which is the synthesis candidate generator, I would say, from msynth. It needs an Oracle path, which is essentially the database. The Oracle path is the database that has those this enumeration, these listings of candidate expressions, and will map them with input-output behavior. We just have this offline. We are loading from a Pickle Python database, which is the way they decided, the authors of this tool decided to store those offline databases. Okay, I think this was here. I have it here. This is one of the databases which has, like, I think it was up to 5 variables, 6 operators, arithmetic and bitwise, and up to 3 levels of derivation. I'm not sure if that's correct, but I think it was that way anyway in the repository to explain. And they also have a download link for another databases with other kinds of construction and combinations of operators and numbers of variables and so on. Okay, now let's just initialize the simplifier, the synthesis simplifier, if you want, with the path to the Oracle. Let's run this. Will take a few seconds to load this database. It's quite a big file. So let's start writing code while this loads. Shouldn't take that much long. What we are gonna do now is, okay, let's pass our miasm obfuscated expressions that we have retrieved from symbolic execution into this program synthesizer, this synthesis simplifier, that will construct a candidate program by means of synthesizing the semantic behavior of each sub-expression of the obfuscated code, only with respect to its input-output behavior, its semantic behavior, not caring about how it's represented in syntax. And then essentially gives us, okay, this is a synthesized candidate which matches the input-output behavior that we have seen for this expression, okay? So the first that we will see, for example, will be the first one, which should give us the very same expression. I think it was that way, right? Racks, symbolic execution. Let's make a format string here. Oh, okay, sorry, I lost the mouse for a second. Again, let's print it again for the sake of completeness. And then let's print the synthesized version. Okay, here, no surprises. The symbolic execution for the first expression retrieves this non-obfuscated expression for the first function. And the synthesis, it hasn't found any simple version of this, expression. So the synthesizer actually what has done is, okay, I'm gonna try to construct a candidate, a program candidate, an expression candidate using a set of operators, in this case, usual bitwise and arithmetic operators, using up to that much number of variables, in this case, 2 variables, which are the number of variables of this expression. And I'm trying to build the simplest expression I can that matches the input-output behavior. In this case, it synthesized. Actually, it learned, if you want, the very same expression, because it's the simplest representation, we could say, for the semantics of this code. So the semantics, the behavior of this function are encoded as simple as possible within this expression, which is the addition of, on one hand, XORing two inputs, on the other hand, ORing the 2 inputs. Okay, but what's interesting is what we'll see now, starting on the second one, the second expression that we obtain from the symbolic execution, and we'll attempt to simplify it to synthesize a candidate that matches its semantic behavior. Okay, here we go. What happened here? So this is the expression that we obtain from symbolic execution. Okay, this is the expression that we obtain by symbolically executing by obtaining the expression for the value of the return register RIX with respect to the input variables, the registers RDI and RSI from the assembly code using symbolic execution. But when we use this expression, this obfuscated expression, this obfuscated code, we treat it and we deal with it only from a semantic point of view, we say, okay, we don't care about the syntactic representation. Let's produce some input and output pairs using that very same expression as an oracle, the obfuscated code, the obfuscated expression, an oracle. So we are just evaluating this expression and generate with a pair of inputs and retrieving the output and getting a list of pairs of inputs and outputs. Now let's just use that knowledge to build, to learn, to synthesize a candidate program, a candidate expression, a candidate code that encodes these semantics from a semantics point of view, from the behavior of the code, but we don't care about how it's represented from a syntactic point of view. We just care about its semantic behavior, its actual behavior, not how it is written, how it is actually the number of instructions or the number of terms of the expression. That's why the synthesizer has been able to retrieve the simplest expression in this case. Okay. Now let's take a look to exactly the same for the third and the fourth. That's fourth. Yeah, indeed. This should be sent to actually print it correctly. Yeah, okay. The third expression. This is the third expression. And again, we have been able to synthesize its semantics in the form of the simple expression. Finally, we'll just take a look at the fourth one, just for the sake of completeness. But as you might be guessing, this will give us exactly the same. So here's probably the most surprising. Again, the reason why I am doing this with several versions of the obfuscated code, going through like a monster like this one, you probably won't see anything like that usually. I don't say that I haven't seen crazy things, but it's not very common that you see things that crazy. But the reason I'm insisting again and again, over and over again, is that we are reasoning on the synthesis perspective with the behavior, with the semantics, with the actually get it from the input-output description of the behavior of the obfuscated code. So we can, if we just take into account how it is behaving, it doesn't. We don't care if it's written like in this monster form or if it's written in a super simple form like the original one. We just don't care about how it is written because we are not reasoning about the way it's written, its syntax. We are reasoning about how it is behaving, and the way it is behaving is exactly the same. That's why program synthesis allows us to make this step up of, okay, let's reason actually about the semantics of the code, about how it is behaving, instead of the being limited by the syntax treatment, by SMT, inability to deal with heavily obfuscated MBA transformations or kind of obfuscated code. So let's move from the limitations that impose syntactic reasoning, and let's just try to adapt our techniques, build tools that deal with the obfuscated code from the semantics point of view. This is all, of course, motivated by the fact that when we are obfuscated code, we are protecting such code. We want to preserve, from the point of view of the one who is obfuscating, who is doing the protection, if you want, we want to preserve the semantics, we want to preserve the behavior. You don't want to change the behavior of the simple version. You want to preserve the behavior, but make it way more difficult to extract information and to understand what's happening. So we apply like the inverse reasoning with program synthesis. We want to develop ways, methods that allow us to reason about the behavior, the semantics of the code rather than the syntax. Because if we rather on the syntax, we will never win, I would say, because the attacker can arbitrarily increase the complexity, that algebraic complexity of the expressions, the syntactic complexity of the expressions, and so on. So let me just get back to the slides to finish that, and maybe we can read a couple of questions if we have time. So that's it. I will try to clean a little bit the demo that we have done today and upload it to GitHub. This will be done probably tonight. You should receive, I will share in the Discord, of course, but you should receive an email probably tomorrow with some communication from the R0 crew, and we'll make sure to give them the GitHub link so they can share with you as well. So I will share the Python notebook, the notebook we have been doing, as well as just a couple notes of an environment, the tools you need to install, and how to do that if you want to replicate and play with that. Okay. If you want to know more, as Cherry said at the beginning, I will be giving a full version of this topic, full training, a 4-day training at Ring 0 back to Vegas. The training is an analytical approach to modern binary deobfuscation. We cover everything way more in detail on obfuscation, control flow-based obfuscation, data flow obfuscation, virtual machines, virtualization-based obfuscation, MBA transformations. We go super deep into MBA transformations, brought from an attack and defense standpoint if you want, how to generate such rewrite rules, other function identities and encodings with permutation polynomials and other kind of functions to furtherly obfuscate and increase the algebraic degree of the obfuscation. We use many flavors of SMT-based analysis, symbolic execution, and also we go deeper into more symbolic execution and program synthesis and so on. So if you're interested, I'll be teaching the full training in person at Las Vegas this summer, early August, and you can register and link, and you can also scan the QR code for more information on the registration as well. So that will be all for me. Let me know, Terry, if we have time to answer maybe a couple of questions. I see the chat is moving. I'm not sure I can keep up with everything, but anyway, you can follow me on Twitter. It's at Arnau Gàmez, you've seen it at the beginning, and you can DM me in there, also in Discord, and I will be super happy to chat with you all. So let me know, Terry, if we have time for a couple of questions. Otherwise, you can just contact me.
We have plenty of time for questions.
Okay. So let me just give me a few seconds to read a little bit of the chat. I've seen there has been some movement in there, but I haven't really been paying attention during the talk. Yeah. Okay. Elias says, yeah, resources to generate MBA would be great. Let me see if I have some super quick links. The thing is that the theoretical methods are described in papers. I haven't seen like anywhere with code implemented other than my own private code that I have for that. But I can share with you. Yeah, let me share with you, for example, yeah, might be my bachelor thesis, a self-plug, but I described the method to generate them. Okay, so Elias asked, here you have the PDF. It's my bachelor thesis. You have a lot of stuff that we have talked today. Also, well, you have explanations of the QSynth algorithm and other synthesis approaches and so on. In the part of the MBAs, in particular, you have described the method to generate linear MBA equalities, which allow you to actually generate rewrite rules. I also describe other MBA transformations and obfuscation, not only of expression, but of constant. You have many stuff in there. And even if you don't find like everything to the detail, you have all the references in there. Again, if you really want to know more, want me to point to something super exact, ping me on Twitter, Discord, whatever. And I will be super happy to share more with you. It's just not for me going to find a ton of links right now. Okay, so yeah, someone shared a blog from Quark's lab on obfuscation with Mixed Boolean-Arithmetic. Yeah, this is the thesis from iRolls, which is an awesome thesis. She was she was who started to formalize some of the aspects of MBAs. If you're interested more in the academic research part of the Mixed Boolean-Arithmetic expression, definitely read this thesis. I of course read it a few years ago before starting my bachelor's thesis and so on. I'm gonna repaste it, okay? But it was shared before. Okay. So there is some question that you call simplify the monster.
Sorry to interject, but your chat is set to host and panelists. So you're only showing me the
okay.
The
yeah, sorry. So I see you have reposted my thesis link, so I will gonna send to everyone again the link for the iRoles thesis I was chatting about. Yeah, you should be seeing it now. Then there was the question of the simplify applied to that monster, the Z3 simplified. As you have seen, it doesn't really do anything to it. Then there is the other question, okay, if you compile with O3, which is the maximum level of optimization for the compiler when generating the assembly, what will the result be? Yeah, the result will be smaller, that's for sure. Not that much. In this kind of MBA expressions, you could expect some term grouping. I didn't want to use optimization for a couple of reasons. The first of all is that I showed you the whole process from obfuscation to deobfuscation, but usually you are not the one obfuscating when you are dealing with some obfuscated code. So that's from one part. The other part is that if I use optimization, it wouldn't be that clear, the mapping between the expression we were doing, the C code, the assembly, and the symbolic expression retrieval. And I really want you to follow like the whole flow from like the whole circle. Okay. Another thing is that it would definitely, at least for the first one, it would definitely inline the function, which would make a little bit more tedious if you want to plug the symbolic execution for the function. It was just for the sake of from pedagogic reasons. But yeah, of course, if you use optimization, it will definitely try to condense a little bit the expression on some redundant code. That being said, optimization, either in GCC or Clang or whatever, it cannot really condense significantly obfuscation with strong MBA transformation. In this case, I've only showed rewrite rules. It will it won't, well, we can try that. We have a couple of minutes. Let me just super quickly. Let's go with the monster, okay? O3, let's see what happens. I have no idea what will happen, but I would bet that it won't. It will be smaller, but it won't get rid of that. I think we haven't used like super advanced MBA transformation. We haven't used any polynomial terms, so the expression, even if super big, it's only linear. We have no exponents if you want to think that way. Maybe it got inlined. I don't know. Okay, no, it didn't go in line. Yeah, okay. It's definitely smaller. It's definitely smaller, but it's still massively obfuscated. You cannot understand anything from that. This is the fourth, okay? This is monster. It is definitely smaller. So optimization plays a role. And one of the ways of the obfuscation, one of the approaches to the obfuscation is let's lift the assembly code into some intermediate representation and then apply obfuscation. I apply optimization techniques to this obfuscated code. And this works like a charm, for example, for dead code removal and so on. Again, for example, this is the code that we can retrieve with full optimization on compilation time. It reduced the code. Yeah, definitely. It reduced the code quite a lot. It makes it understandable? Not at all. So you can't retrieve the semantics from that at all. But as I was saying, this now we have the full circle. We are we are the ones obfuscating, and the obfuscating, the attacker or the one who is obfuscating can do whatever it wants. So you don't really have the ability to reason to deal with that. But as you mentioned that, I wanted to point out that applying compiler optimization techniques is one way of dealing with obfuscation, not really with MBI transformation. They are not that useful, but with other kinds of obfuscation techniques, like, as I was saying, dead code removal or constant folding or constant propagation. It works like a charm applying such techniques. There is another question. It says, what's the difference of executed with Ghidra P code? I'm not sure what you're referring. I'm not super familiar with Ghidra, honestly. There is a link to video. Well, okay. Honestly, I'm not sure because I don't really know what do you mean. I'm not super familiar with Ghidra myself. But with Ghidra P code, I know it's the intermediate representation that uses Ghidra for the compiler to produce the decompiler output. And when you say the execute, I assume that it must have an interpreter. Ghidra itself or another tool should have an interpreter for the P code itself. So it's really, it's similar in the sense of you are dealing with an intermediate representation, but it's not the same in the sense of with symbolic execution. What we are actually doing is taking the variables and making them symbolic variables, not actual variables. And this makes a lot of sense. So this is super crystal clear when we are doing control flow analysis. In this case, it was simple data flow with a basic block. But when we are doing control flow analysis, where we have actual code which is branching, we are actually saving two different maps for the two different branching conditions, the branching basic blocks, and we can compare symbolically, okay, what is the constraints that would make it go to that branch? What are the constraints to that other branch with respect to the symbolic expression? So I'm not sure if I am answering your question with respect to Ghidra P code. I'm not super familiar with that, but just so you know, one thing is executing, evaluating an intermediate representation, which Miasm can do. It has an emulator for its own intermediate representation if you want. And the other one is, let's deal with code as if it were like symbolic values, not dealing as real values as execution, but as symbolic values that we can track them, we can fork them for account for different states. And again, this is super clear with control flow, and we deal with control flow. There's another question for the synthesis part. Says, was the pickled oracle generated beforehand? Does it ship with oracles? Yes and yes. So the yeah, actually, you should just afterward the oracle. This is exactly the oracle I use, the one that gets included in the GitHub as well. They have in the repository. They have in the repository as well a link to 31 or 32 gigabytes of other Oracle databases. But this is the one I used and what's sufficient for this approach. And I haven't generated my own, not in MSynth. I have my own like bare bones prototypes, but not really integrated within any symbolic execution engine yet. But the authors of MSynth, I think Tim and Moritz, they didn't share yet. I'm not sure if they have intention to do so. They didn't share the code to generate such databases. So they shared some of the pre-computed databases. This one that I've used, which is the basic one, I would say, if you want, and also a big file with some other databases. But as far as I know, they haven't shared the code to generate such databases. So there's one question, how much does picking a good oracle matter in program synthesis? Could you get wrong, not simplified results if you pick a wrong database? Totally. So in this case, just one thing first. This is a particular flavor of program synthesis based on the QSynth algorithm, which uses offline tables databases to enumerate possible candidates. There are other approaches to program synthesis. There are some like more stochastic approaches with Monte Carlo tree-based Monte Carlo searches. For example, Cynthia was an approach. What happens is that QSynth proved to be extremely successful and extremely fast. And they introduced a way to deal with expressions by means of synthesizing sub-expressions, which makes it super powerful. But yeah, definitely. If there is one big point in here, and there is like an academic question is, if I have a super obfuscated expression, for example, what is the minimum set of operators and variables that I need to represent its semantics independently, regardless of how they are combined? And that could lead into how to generate a database in this particular flavor of program synthesis that can encode their semantics. That being said, in practice, barely, like almost all the code that you can find out there can be, which is obfuscated in the sense of, let's get something semantically simple and make it syntactically complex. Okay, you can retrieve it with quite basic databases of that on, because with the basic operators you can essentially capture the semantics of all pretty simple semantic code. Okay, but yes, more from an academic point of view, if you want, picking the number of operands, operators, and the number of derivations for the database can play a role, of course. And if you essentially, if your database of oracles in this scenario is not able to generate, doesn't contain a semantically equivalent candidate expression for the code you're trying to synthesize, you are not going to accomplish it. It's quite hard to find such scenarios in practice. I mean, most time in practice, I found that it's pretty, like, you're good to go with pretty basic databases, because people they are obfuscating super basic operations. This is, you have to think this kind of MBA transformations or obfuscation are usually a part of a greater virtualization-based obfuscation, where they invent a particular instruction architecture set, and then they obfuscate each one of the operations of this virtual machine. So the addition, the subtraction, the XOR. So usually you find that you're synthesizing essentially operations of one iteration most of the time, or very, very simple, because those are usually the contexts where this obfuscation in real life, in software protection, either in malware or commercial software protection, this is usually the cases where it's used. So I see Elias is answering before. Okay, so you can symbolic execute with Ghidra. Yeah, I didn't know that. That's good to know. So I think it was referring to the previous question about comparing with the P-code execution. So yeah, Sergio says, I'm not sure I have understood everything you presented, and I know how fantastic it was. So again, this recording will be uploaded. The slides have been super short because I wanted to go straight to the live coding. You can revisit it again. I have tons of materials. If you check my talks, there is my repo on GitHub, Arnau Gàmez talks. It's super easy to find. You have a lot of talks and other workshops and so that I've done, going more in detail in those aspects, especially the MBA part. You can check that out. And also you can reach me, and honestly, leave me a message on Discord, on Twitter, wherever you find me. And I'll be super happy to help any one of you and to chat with you on any doubts or any ideas on me, anything you have to say about it. So, do you have an idea to tell the scramble 3 and scramble 4 do have the same semantic or some probability guess? Yeah. So this is a super nice question, because as I've said, I'm not checking it with Z3 because the SMT solver would have really hard time doing that, checking the semantic equivalence. There is a super nice research, super recent as well, which is called MBA Solver, which I don't really want to go super deep into that, but very briefly, it allows us to transform arbitrary MBA expressions into a form which is more digestible by SMT solvers. And by doing so, SMT solvers have a better chance, and actually works pretty nicely, have a better chance to prove the semantic equivalence of this expression against the other one. I've done that with my master's thesis, which is not public yet, but I don't mind sharing, like probably in a couple of 3 weeks, it will be public and I will share around. So if you follow me on Twitter or GitHub, whatever, we'll upload everywhere, where I actually integrate this MBA solver approach within a workflow of, let's retrieve an expression with symbolic execution, let's synthesize a candidate, and then let's verify actually that the candidate is semantically equivalent, is correct if you want for that. this is a cool way, more academic-ish if you want, but it works really nicely because by means of the MBA solver part, this prototype, we are able to reduce the obfuscated expression into a normalized version, if you want, which is not, usually it's not the simplest version, but it's a version with some particularities that make it especially suitable for SMT solvers to deal with. Let me share with you the paper if I find it super fast. Yeah, I'm not finding the paper right now, but I have the GitHub repository, and if you find the paper for this repository MBA solver, you can read the paper and play with the prototype as well. This essentially transforms an obfuscated MBA expression into a normalized version, which is more digestible by an SMT solver. Let's put it that way. Okay. I think that's all for me. Yeah. So if I missed something, sorry, I just skimmed over it. You can again reach me over Discord, on Twitter, wherever you find me. Just draw me a mail, whatever works for you, and I'll be super happy to chat with you all and have a nice talk with all those topics. Really, I have no problem chatting with you all and sharing any resources of anything you're more interested. And again, as I was saying, this has been done in collaboration with Drink Zero, and I'm offering a full training with them early August in Las Vegas. So if you are really interested in that, you could also think about signing for this training. That's it for me.